Hello students, welcome to all. Today our new topic under the electrostatics, electric fields due to a circular loop of charge. This is a our circular loop. Also we can also say that a ring. I have given some charges, positive charges. You can give any type of charges, whether it is a positive charge or negative charges. We need to find out the electric field. The electric fields due to these circular loops at the point of P. So this is our three-dimensional pictures. So we have placed this ring parallel to the YZ plane. This is parallel to the YZ plane. If you imagine this ones, so this is a your YZ plane. YZ plane should be normal to the x-axis. This is your x-axis. YZ plane is the normal. On the YZ plane, x-axis will be your normals. So let us take a small piece. Take an elementary piece of the ring AB. Suppose if I take this is elementary, a small piece of the ring, and this point is CB, AB. AB, a small piece of the circular loop. So we have to find out this is taken a positive charges. We have to find the electric field at this point, this one. Since this is a positive charge will have electric fields away from the charges. Therefore, the electric field due to this positive charges will be away from these ones. Now, let us suppose electric field due to this ones is along this one, DE. So DE the electric fields due to this elementary piece AB. So it makes an angle theta with x-axis. This is vertically opposite. So if I give the total charges, Q is the total charge given to this ring. So how much the charges given to this piece AB? So we have to find out charge density per unit length. Let us charge density here. Charge density will be charge divided by length. Here total charge I have given. Let us suppose total charge given is Q, and length of this ones. Length of this circumference of the ring is 2 pi a. 2 pi a will be the length. So a is the radius of this ring. A is the radius. We need to calculate electric field at the point of P. Let us suppose OP is equal to x, and this distance is x. So and length of AB, ACB, arc ACB. This is the arc ACB. Have the length DL. So total charge on this length will be dq. dq will be the charges. You multiply this charge density. This is, let us suppose, lambda. Lambda times of charge per unit length is lambda, also known as Q upon twice pi a, known as charge density, charge per unit length. Its length is dl. Total charge on this will be lambda times of dl. So lambda times of dl. So put the value of lambda here. Q divided by 2 pi a multiplied dl. So we know that from the Coulombic laws, electric fields produced by this elementary piece at this point P will be. So D is equal to 1 upon 4 pi epsilon naught charge, this is dq, divided by the distance. So what will be the distance? By using the Pythagoras. So this is a, this is x, and this will be root a square plus x square. A square plus x square will be the distance of CP. So now look at this picture. Since electric field is a vector quantity, so it has two components. D has two components. One is along the x-axis, another is normal to the x-axis. Normal to the x-axis will be along z-axis. So any line which is normal to, since we need the electric fields along this direction, so it will be this directions which is normal to the x-axis will be parallel to the z-axis. So if I breaking this component in two parts, this will be our normal component. So one component will be along this one. We said the DEN. So DEN will be D times of sine theta. Another component will be along x-axis. So let us suppose this is along x-axis DEX. It will be DE cos theta. Let us represent it component along DEX along x-axis. So these are the two components. So now if I take just opposite of this one, vertically opposite of this one, AB. So its electric field will be at this point is along this one. If I take just opposite of diametrically opposite piece of AB will be here. Suppose this is A dash B, A dash B dash. Yes, this is the diametrically opposite of this one. So its electric field will be along this one. If I break in this one, yes, it has also the component along this one. This component should be broken into two parts. So this is obviously an angle theta. This is symmetrical one. So this is the electric field which is produced by A dash B dash. Electric field produced by this elementary particles A dash B dash. Its direction will be along this one. Now this will have also two components. One is along x-axis, another one along this one. So this component which is normal to this one, if I represent this one, this is again vertically opposite angle. Vertically opposite angles. So this component can be broken into two parts, along x-axis, along normal to the x-axis. Normal to the x-axis will be parallel to the y-axis. So this component can be this is again theta, and this has value now d dash, and normal to this one will be de dash sine theta. So another component will be along this one, that will be component of DE. So will be d dash cos theta. So d dash cos theta, all the component which is along the x-axis will be added. We can add all these components, and those components which is normal to the x-axis will be cancelled out. So every in this circular path, every piece have diametrically opposite piece also. They will cancel the normal component which is along x-axis, which is normal to the x-axis, will be cancelled out. Similarly, if I take one piece along at this point, another piece along this one, they will also produce two component. One component goes along x-axis, another component normal to this one. Normal to the x-axis component will be cancelled out. The total electric fields at this point P, due to this circular ring, will be along the x-axis. It means along px, along the px directions. So we have to add all the component, which is along x-axis, and then it will be now put the values here. The electric field we take only one piece, due to one piece along x-axis, then take the integration of this one. Now dq divided by this distance, square of this one will be square of this one, a square plus x square. Square of this will be, it means that Cp whole square will be this one. Now we need the component only along this one. So dx. Now if I take dx, so it will be d cos theta, d cos theta. So now d cos theta. So since here the electric field produced by this is d, and electric field produced by d dash, both are equal in magnitude also. So d and d dash both are equal because they are equal distance and same amount of charge is carrying. So 1/4 pi epsilon naught, the charge will be the same ones, and square of whether you take Cp and this is C dash P will also the same one. So this is again a square plus x square using the Pythagoras, using the Pythagoras theorem, this triangle. So 1/4 pi epsilon naught multiply dq upon distance of Cp square. So whether you take Cp and Cp dash will have the same value. So now this is the x component of this one. Total electric field produced at the point of P will be taken the integration of this one. Total electric fields at the point P is equal to, if I represent this by E, now this E will be integrations of this value. So this value will be 1/4 pi epsilon naught, and the charge dq, put the value of charge which is dq, this is the dq. dq has this amount q times of 2 pi a into d lambda, and divided by over a square x square, a square plus x square, and you have to find out the value of cos theta from this triangle. From this triangles, if I take the cos theta here, cos theta will be here from the triangle. Triangles COP, cos theta will be OP divided by, cos theta will be OP divided by CP. Our OP has the value, x, and CP has the value this one. So this will be a square plus x square. If I multiplied here that value, x divided by a square plus x square. Now the value which is a constant taken out of the integration. Now therefore the electric field will be here 1/4 pi epsilon naught q upon twice a, q is constant, 2 pi is also constant, and this value is also constant taken out of the integration. X divided by this one, a square plus x square, its power is 1, and if you add these values, 1 plus its power is 1 plus half will be 3/2, 1 plus half, and into dl should be inside of the integration of dl. So integration of dl, this piece has the length of dl. I have taken, so its length is dl. If you hold pieces of the circular ring, so then it will be total length of this circular path will be the circumference of this ring, which is 2 pi a. So we have replaced these values by 2 pi a. Now just simplify this ones. It comes out 1/4 pi epsilon naught, 4 pi epsilon naught into qx in the numerator divided by 2 pi a, and into a square plus x square raised to the power 3 by 2 and multiplied with this value comes out. This value will be integration of d will be 2 pi a. So you multiply this by 2 pi a. Now just simplify this whole terms cancelled. So finally we have the value of electric fields. Electric fields at this point P finally get this value 1 upon 4 pi epsilon naught to qx divided by a square plus x square raised to the power 3 by 2. Now it's all component have the electric fields along px. So its directions will be along we say the op. So its direction will be along op. This op will be the op is normal to this circle. This is op normal to this circles. So this is the final value of the electric fields. If I take some cases of these ones, now what will be the electric field at the point of now taken some two cases we have here. First one, we should remove this one. Yes, case number 1. Case first. So at the center of the ring, O is the center of the ring. If I place x equal to 0 at the center, of the ring, x will be 0. This is the circular loop like a ring. So if I place x equal to 0, now x equal to 0 in this expression, the electric field will be 0. So it means that electric field at the center of this circular loop is 0, because so here all pieces. So if I say that electric field due to at this point due to the away from this one, it will be away from this one. At this point, every piece diametrically opposite piece will have electric field at the point of O in opposite direction. So they will cancel each other. Now case number 2. Now case number 2, if x is very far from the circular loop, it means that when x greater a, if I compare with this radius of the circular path, if x greater a, so in that case our electric fields will be, we just left a square. Okay, if I remove a squares from, because a tends to 0, if I compare with a is very small, so we have to place a equal to 0 in this expression. So finally we get the value 1 upon 4 pi epsilon naught. So here qx in the numerator over a square will be 0 plus x square raised to the power 3 by 2. Now if you simplify this one, this value comes out 1 upon 4 pi epsilon naught. So q upon 2 and 2 is cancelled out, x cube. Now finally this is the final answer of this one, 1 upon 4 pi epsilon naught q divided by x square. So this values like a point charges we have placed at the center of this one. We suppose that if this x is far from this circular path, then this circular loop behave like a point charges, and that point charges resides at the point of O. So now that these are the two cases. Now electric lines of force. In electric fields we can define some lines of force. they are imaginary, and they will give us the amount of the magnitude of the electric fields and the direction of the electric field at a particular point. Now if I define the electric fields if I place a unit positive charge, suppose this is the point P. If I take, suppose the electric field lines can be, first thing, straight lines, they can be straight lines, and they can be curved line also. So in the case of the curved lines, if this is these are two types of the electric lines of forces. If I place a positive charge, suppose if I bring a positive charge, if I place a positive charge here or here, so this positive charge will move along the direction of the field lines, and this is a covered field lines. So any electric field lines, these are imaginary lines. If any positive charge is free to move on these lines, so it will goes along these lines. So so here this is a straight line. Electric field has the directions of along these ones. If I find the directions, direction of the electric field on the curved path, we should have taken a tangent here. If I draw the tangent here, so the electric field will be along this one. So every point in this curved part have different direction of the electric fields, and the magnitude of the strength of the electric fields will depends on the number of field lines crossing a unit area. Suppose if I find out this is a unit area, if the field lines crossing this, so the number of field lines crossing normally, these are the field lines, will give you the strength or magnitude of the electric fields at this region. The field lines, these are the field lines. So there are some important properties we have to discuss. Properties of the electric field lines. Let us define electric field lines. A definition of the electric field lines. An electric field lines electric field lines of force. Electric field lines of force is the path traveled by a positive charge if free to move, if let free to move. So yes, so this is if I place a positive charge in a electric field regions, it will goes along this path. If the field lines are straight lines, then the positive charge will move along the direction of the electric fields. So now properties of the electric field lines. So first one, electric field lines, they originate from positive charge. Positive charge, it means that they start from the positive charge and terminates on a negative charge. So it means that there is a positive charge here, This is q1, this is negative charge q2. They start from here and they terminate on the negative charges. They are not continuous. Okay, they start from positive and end at the minus q2. They never come in a closed path like the magnetic field lines. These are the discontinuous lines. They start from plus and end at minus q. Now second property, they never cross each other. They never intersect each other. Now they to look at this point P. This is the P point. They will never intersect. Never intersect means, so here if these are the two field lines I have drawn here. This is the point P. At the point of P, so we can draw, if I find the electric field at this point, so its direction should be along this one, and this is the second direction. So electric field at the point of P will be there are two direction of the electric field, which is impossible. Electric field should be only one direction and one magnitude at a particular region. So it is not possible. They will not intersect each other. Now third point, they cross the surface normally. They will cross. Surface normally. Surface means like a conductor. Now property number 4. We can define they cross the surface normally. Suppose this is the, if I take this positive surface, so electric field lines should originate normally. They originate normally on the surface of the positive charge. Likely there is a negative surface. Suppose this is negative surface, so electric field lines should normally end. They will end because this is negative charges. So they should have normally end on this negative surface charge. Now fourth point. So in a conductors, now fourth point of this one, there is no field lines. Field lines never cross a conductor. Never cross a conductor. Because there is no electric field inside it. This is a conductor. Suppose whether it is a hollow ones and solid one. If this is made of this one, so this is like conductor. If I give some charges of this one, suppose given the positive charges, so there they originate, the positive charges would remains on the surface, outer surface of this conductor. They originate electric field lines and never cross this this conductor. Okay, they just come out normally will come out, but they will not never cross this one. Now fifth point, they contract lengthwise. So we can say that longitudinally they contract. They contract longitudinally. Longitudinally, and we can say that uh, longitudinally or lengthwise. So I give the examples of this one. So suppose there is a this is a positive charge, another is negative charges. So we know that the field lines originate. This is positive charges and this is negative charges. Suppose Q dash. So this goes straight and so this band along this one they contract lengthwise. They contract lengthwise. The field lines originate from the positive charges. This is our positive charge. This is our negative charges. So contract lengthwise means yes they band lengthwise. Now sixth point. The lines of force exerts pressure. Lines of force exerts pressure on each other. So it means that between two like charges, they can exert pressure. Suppose this is positive charge, this is also positive charge. If I draw the line of forces, they originate from positive charge. They originate from positive charge because there is also positive charge. There would be Coulombic repulsion between them. So it moves along this one. This goes along this one like this. So here, so this field lines repelling the field lines of these charges. So it can also define the repulsion between two like charges. Now seventh property of this one, relative closeness. Relative closeness gives us the strength or magnitude of the field lines. Relative closeness gives the strength of the electric fields. It means that where the field lines are a lot of and the strength will be more, and where the field lines is less, the strength will be weaker. Let us draw some field lines. Suppose this is the verb. These are the field lines. So I've taken 2 points. Okay. So here, so this is the point of A. This is another point of B. So here at the regions of where the point of A, at these regions the field lines are very close to each other. At the point of B, the field lines are spaced, they are far from each other. Okay, so therefore the strength at E is more than that of the strength at the point of B. So therefore electric field at the point of E is more than that of the electric field at B. So these are the properties of electric field lines and they can give some ideas about the direction and magnitude. Suppose field lines in case of a point charges, if I have the positive charges here, this is about the positive charges, field lines will be straight away from this one, normal should be field line normal on the surface of the charges. So these are the field lines of these positive charges away from this one. They originate from the positive charge and end on the negative charges. So if I take the negative charges here, so now this is our negative charge. It's a field lines. Its field lines will be normals, and end on the negative charge. They should be toward the negative charge and normal to this one. So normal to this one. So next there are group of charges. Second point we have feed lines. In case of a group of two charges, we have two charges. Yes. So now if I take one is a positive charge, this is let us suppose this is our positive charge and this is our negative charge. So we know that feed lines originate from positive and end on the negative charge. Yes, here it goes straight and it will bend. Like this, away from this one, curved also, and coming from some positive charge at infinite. Yes. So here they are lengthwise contract. That's why between plus and minus charges there are attractions. If I take both are positive charges or both are negative charges, suppose these are negative charges, both are like charges, they will take pressures on each other. So it will go in the negative charges. These are in along this ones. They will also like this one ending, because this is negative charges coming from some positive charge at infinite place. So they will end on the negative charges. These are the field lines. So coming from some positive charge at infinite place, and yes. So in this way the field lines of this negative charge exerting the pressure on the another negative charges. That's why between the like charges there is repulsion, and between unlike charges there is attraction.